Hi guys, so let's talk about thermodynamics. I'm going to break this into several shorter videos because there's about 36 slides to go through. Okay, and I will post this eventually to Plus Portals. So we have 4 sections in this and we need to go over all 4. We're going to start with spontaneity. Will a reaction occur without intervention? Will it be spontaneous? And that's a big question because if we have to apply energy into a system, it may not be feasible to do that reaction. Or if it occurs naturally, do we want it to occur naturally or do we want to be able to stop it? These are really good questions, especially on a big plant scale where lots of energy and heat could be required or given off. So we want to be able to answer this question. A spontaneous reaction will just happen. It doesn't mean that we don't have to give it a start. For instance, if we look at hydrogen in the presence of oxygen, if we give it a spark, then that reaction will go without intervention or it will be spontaneous. AP does not like the word spontaneous. They've gone away from that. So just letting you know. It is important not to confuse spontaneous with fast. They can be very slow. So we will study kinetics, which is a different chapter, chapter 12. We're not there yet. It's coming soon, though. So if a reaction is spontaneous in one direction, given the example I gave you earlier, the reverse reaction is by definition non-spontaneous. It means it will not occur unless I supply energy. And so in class, I'll give you an example of the second one where we take water and we can decompose it into hydrogen and oxygen, but I have to give it energy, so I use a battery to do that. So many spontaneous processes proceed with a decrease in energy. That means they are spontaneous reactions are often exothermic, but not always. As we know, if we take one of those cold packs, break the inside ampule, shake it, it gets very cold. Well, that would be an endothermic reaction that is spontaneous. So it's not necessary, but often. So which of these processes is spontaneous at room temperature? Taking ice and making it into water as a liquid has a delta H of positive 6.01 kilojoules per mole. Taking liquid water and making it into ice as a solid has delta H of negative 6.02. So here's another example of a non-spontaneous reaction that is exothermic, the second one. The one that is spontaneous would be the first one. We know that just from life, that ice melts to water at room temperature. So when we have two objects that have different temperatures, in this case X is hotter than Y, when we put them in thermal contact, make them touch, then the two objects will come to a average temperature, but there will be no change in energy, but the heat does spontaneously flow from one object from the hotter one to the colder one. Some other factors other than energy is important for a spontaneous process. It appears greater, more uniform dispersal of matter, and energy can be the driving force for a spontaneous reaction. So that factor is called entropy, which is kind of the disorder or randomness of a system. So entropy is another state function, just like delta H. Enthalpy is a state function. It makes no difference how we get from point A, the initial, to the final. The change in the system will always be the difference between the final minus initial. Same thing with delta H. I could go through 6 reactions, and if I got what I wanted from the start to the finish, then it would be a state function, and I could calculate the enthalpy. I could also do the same thing for entropy. Other factors that include entropy are the phase of the substance. Solids are the most ordered, liquids are less ordered, entropy increases finally as a gas. The temperature of the substance. If the temperature is increasing, then the particles have more energy, they can move faster, and they can have more random states, or they can move around more, so that would also increase the entropy. So here we have some diagrams. The crystalline solid is the lowest in entropy, the liquid be next in the middle, and then gases would be the most disordered. And so if you look at an equation and you look at the reactants to the products, if there are more gases, moles of gases as a product, entropy is increased for that reaction. If it goes from a gas to a solid or a liquid, then entropy would decrease for that system. Does not mean it will or will not be spontaneous. So here's just another graphic for that. There is a lot of entropy that changes at the melting point and boiling point, and then as we add more temperature or more heat to the system, it increases in entropy as well. The third influence or factor is the type and number of particles that make up the substance. If we have more particles, it has more disorder than if we have fewer particles. So if you're looking at a reaction and you have only 5 moles for the reactant, but you have 10 moles for the product, then entropy is increased in that reaction. And variations in the types of particles is also an influence. Do you have pure substances and then you dissolve it into maybe an aqueous solution, now you have a mixture, then that would give you an increase in entropy as well. So we've talked about the system as a part of the universe of which we are interested. And the surroundings is everything else. And the sum of those two is called the universe. So correctly predicting the spontaneity of a process requires us to consider the entropy changes in both the system and the surroundings. So the change in entropy for the universe is equal to the change in entropy for the system plus the change in entropy for the surroundings. And this is the second law of thermodynamics. And it states that all spontaneous changes cause an increase in the entropy of the universe. For a spontaneous process, delta S for the universe must be positive. In a process with delta S that is negative for the system, it can still be spontaneous if we have an increase in enthalpy. So, delta S for the universe is greater than 0 for all spontaneous processes. Delta S for the universe is less than 0 for a non-spontaneous process. And delta S for the universe is equal to 0 for a process at equilibrium. And delta G, which we're getting into next, will also be 0 for a process at equilibrium. So our third law of thermodynamics is that the entropy of a pure, perfect crystalline substance at 0 Kelvin is 0. We have not yet reached 0 Kelvin, but it would be where there's no lower temperature, so the particles are no longer allowed to move. All molecular movements completely stop, and there's only one possible way to arrange the molecules, so that would give us entropy would be 0. It is possible to determine the absolute entropy of a substance, and we have them compiled in tables for you. I know you're excited. Standard entropies would be denoted as S naught, and 298 means it's at room temperature, 25 Celsius. The values for 1 mole of a substance at a pressure of 1 bar at a temperature of 298 Kelvin, and aqueous solutions would be at 1 molar. And we can then calculate the change in a reaction using those values, and we would do it just like we've done for enthalpy. And so you would look them up in a table here. You'll notice one thing right away. Entropies are not 0 for an element in its standard state. nor are they zero for any compound. In fact, we never reached zero entropy. So you would look up the values and you would do it just like you've done it for enthalpy. As you see here, the change in the enthalpy of the products minus the change in enthalpy for the reactants. Again, final minus initial. And you would multiply by the number of moles. You have to use a balanced equation. So the second law of thermodynamics can be used to predict spontaneity, but measurements of the surroundings are seldom made. This limits the use of the second law of thermodynamics, but it is convenient to use a thermodynamic function that focuses just on the system and predicts spontaneity. So we need free energy instead. And we've stated this as a law of second law of thermodynamics, but this is the one we use to predict whether a reaction is spontaneous or not. And it's called Gibbs free energy, or delta G. And delta G equals delta H, which is enthalpy, the change in enthalpy, minus the temperature times the change in entropy. Since we can look up delta H in a table, and we can look up delta S in a table, and we know the temperature we're doing this at, we can then calculate the free energy and determine whether this reaction is predicted to be spontaneous or not. Interesting to note, however, is that entropy units are in joules per mole, and enthalpy is in kilojoules per mole. So when you calculate these values, you have to change entropy to kilojoules. So if delta G is less than 0 or negative, then the reaction is spontaneous in the forward direction. If delta G is positive, the reaction is not spontaneous in the forward reaction, and it would be spontaneous in the reverse direction. And if delta G is 0, then the system is at equilibrium. I'm going to stop here and come back to this.